Solubility is the property of a solid, liquid, or gaseous chemical substance called solute to dissolve in a solid, liquid, or gaseous solvent. The solubility of a substance fundamentally depends on the physical and chemical properties of the solute and solvent, as well as on temperature, pressure and the pH of the solution. The extent of the solubility of a substance in a specific solvent is measured as the saturation concentration, where adding more solute does not increase the concentration of the solution and begins to precipitate the excess amount of solute. The solubility of a substance is an entirely different property from the rate of solution, which is how fast it dissolves. Most often, the solvent is a liquid, which can be a pure substance or a mixture. One may also speak of solid solution, but rarely of solution in a gas. The extent of solubility ranges widely, from infinitely soluble such as ethanol in water, to poorly soluble such as silver chloride in water. The term insoluble is often applied to poorly or very poorly soluble compounds. A common threshold to describe something as insoluble is less than 0.1 grams per 100 milliliters of solvent. Under certain conditions, the equilibrium solubility can be exceeded to give us a called supersaturated solution, which is metastable. Metastability of crystals can also lead to apparent differences in the amount of a chemical that dissolves depending on its crystalline form or particle size. A supersaturated solution generally crystallizes when seed crystals are introduced and rapid equilibration occurs. Phenyl salicylate is one such simple observable substance when fully melted and then cooled below its fusion point. Solubility is not to be confused with the ability to dissolve a substance, because the solution might also occur because of a chemical reaction. For example, zinc dissolves in hydrochloric acid as a result of a chemical reaction releasing hydrogen gas in a displacement reaction. The zinc ions are soluble in the acid. The smaller a particle is, the faster it dissolves, although there are many factors to add to this generalization. Crucially, solubility applies to all areas of chemistry, geochemistry, inorganic, physical, organic and biochemistry. In all cases it will depend on the physical conditions and the enthalpy and entropy directly relating to the solvents and solutes concerned. By far the most common solvent in chemistry is water, which is a solvent for most ionic compounds as well as a wide range of organic substances. This is a crucial factor in acidity, alkalinity and much environmental and geochemical work. IUPAC definition. According to the IUPAC definition, solubility is the analytical composition of a saturated solution expressed as a proportion of a designated solute in a designated solvent. Solubility may be stated in various units of concentration such as molarity, molality, mole fraction, mole ratio, mass per volume and other units. Molecular view. Solubility occurs under dynamic equilibrium, which means that solubility results from the simultaneous and opposing processes of dissolution and phase joining. The solubility equilibrium occurs when the two processes proceed at a constant rate. The term solubility is also used in some fields where the solute is altered by solvolysis. For example, many metals and their oxides are said to be soluble in hydrochloric acid, although in fact the aqueous acid irreversibly degrades the solid to give soluble products. It is also true that most ionic solids are dissolved by polar solvents, but such processes are reversible. In those cases where the solute is not recovered upon evaporation of the solvent, the process is referred to as solvolysis. The thermodynamic concept of solubility does not apply straightforwardly to solvolysis. When a solute dissolves, it may form several species in the solution. For example, an aqueous suspension of ferrous hydroxide Fe2 will contain the series iron 1 hydri2O XX+, as well as other species. Furthermore, the solubility of ferrous hydroxide and the composition of its soluble components depend on pH. In general, solubility in the solvent phase can be given only for a specific solid that is thermodynamically stable, and the value of the solubility will include all the species in the solution. Polarity. A popular aphorism used for predicting solubility is, like dissolves like, also expressed in the Latin language as similia similibus solventa. This statement indicates that a solute will dissolve best in a solvent that has a similar chemical structure to itself. This view is simplistic, but it is a useful rule of thumb. The overall solvation capacity of a solvent depends primarily on its polarity. For example, a very polar solid such as urea is very soluble in highly polar water, less soluble in fairly polar methanol, and practically insoluble in non-polar solvents such as benzene. In contrast, a non-polar lipophilic solid such as naphthalene is insoluble in water, fairly soluble in methanol, and highly soluble in non-polar benzene. In even more simple terms, a simple ionic compound such as sodium chloride is easily soluble in a highly polar solvent, and negative charges in the covalent molecule, such as water, as thus the sea is salty as it accumulates dissolved salts since early geological ages. The solubility is favored by entropy of mixing and depends on enthalpy of dissolution and the hydrophobic effect. The free energy of dissolution depends on temperature and is given by the relationship delta G equals delta H T delta S. Chemists often exploit differences in solubilities to separate and purify compounds from reaction mixtures, using the technique of liquid-liquid extraction. This applies in vast areas of chemistry, from drug synthesis to spent nuclear fuel reprocessing. Rate of dissolution. Dissolution is not always an instantaneous process. It is fast when salt and sugar dissolve in water, but much slower for a tablet of aspirin or a large crystal of hydrated copper sulfate. These observations are the consequence of two factors. The rate of solubilization is related to the solubility product and the surface area of the material. The speed at which a solid dissolves may depend on its crystallinity or lack thereof in the case of amorphous solids, and the surface area and the presence of polymorphism. Many practical systems illustrate this effect, for example in designing methods for controlled drug delivery. Critically, the dissolution rate may depend on the presence of mixing and other factors that determine the degree of undersaturation in the liquid solvent film, immediately adjacent to the solid crystal. In some cases, solubility equilibria can take a long time to establish. In practice, it means that the amount of solute in a solution is not purely determined by its thermodynamic solubility, but also depends on kinetics of dissolution. The rate of dissolution and solubility should not be confused, as they are different concepts, kinetic and thermodynamic respectively. The solubilization kinetics, as well as apparent solubility, can be improved after complexation of an active ingredient with cyclodextrin. This can be used in the case of drug with poor solubility. Importantly, relatively low solubility compounds are found to be soluble in more extreme environments, resulting in geochemical and geological observations of the activity of hydrothermal fluids in the Earth's crust. These are often the source of high-quality economic mineral deposits and precious or semi-precious gems. In the same way, compounds with low solubility will dissolve over extended time, resulting in significant effects such as extensive cave systems or karstic land surfaces. Quantification of solubility. Solubility is commonly expressed as a concentration, for example, as G of solid per kilogram of solvent, G per dl of solvent, molarity, molality, mole fraction, etc. The maximum equilibrium amount of solid that can dissolve per amount of solvent is the solubility of that solid in that solvent under the specified conditions. The advantage of expressing solubility in this manner is its simplicity, while the disadvantage is that it can strongly depend on the presence of other species in the solvent. Solubility constants are used to describe saturated solutions of ionic compounds of relatively low solubility. The solubility constant is a special case of an equilibrium constant. It describes the balance between dissolved ions from the salt and undissolved salt. The solubility constant is also applicable to precipitation, the reverse of the dissolving reaction. As with other equilibrium constants, temperature can affect the numerical value of solubility constant. The solubility constant is not as simple as solubility. However, the value of this constant is generally independent of the presence of other species in the solvent. The Flory-Huggins solution theory is a theoretical model describing the solubility of polymers. The Hansen solubility parameters and the Hildebrand solubility parameters are empirical methods for the prediction of solubility. It is also possible to predict solubility from other physical constants such as the enthalpy of fusion. The partition coefficient is a measure of differential solubility of a compound in a hydrophobic solvent and a hydrophilic solvent. The logarithm of these two values enables compounds to be ranked in terms of hydrophilicity. The energy change associated with dissolving is usually given per mole of solid as the enthalpy of solution. Applications. Solubility is of fundamental importance in a large number of scientific disciplines and practical applications, ranging from ore processing and nuclear reprocessing to the use of medicines and the transport of pollutants. Solubility is often said to be one of the characteristic properties of a substance, which means that solubility is commonly used to describe the substance, to indicate a substance's polarity, to help to distinguish it from other substances, and as a guide to applications of the substance. For example, indigo is described as insoluble in water, alcohol, or ether but soluble in chloroform, nitrobenzene, or concentrated sulfuric acid. Solubility of a substance is useful when separating mixtures. For example, a mixture of salt and silica may be separated by dissolving the salt in water and filtering off the undissolved silica. The synthesis of chemical compounds by the milligram in a laboratory, or by the ton in industry, both make use of the relative solubilities of the desired product, as well as unreacted starting materials, byproducts, and side products to achieve separation. Another example of this is the synthesis of benzoic acid from phenyl magnesium bromide and dry ice. Benzoic acid is more soluble in an organic solvent such as dichloromethane or diethyl ether, and when shaken with this organic solvent in a separatory funnel, will preferentially dissolve in the organic layer. The other reaction products, including the magnesium bromide, will remain in the aqueous layer, clearly showing that separation based on solubility is achieved. This process, known as liquid-liquid extraction, is an important technique in synthetic chemistry. Recycling is used to ensure maximum extraction. Solubility of ionic compounds in water. Some ionic compounds dissolve in water, which arises because of the attraction between positive and negative charges. For example, the salt's positive ions attract the partially negative oxygens in H2O. Likewise, the salt's negative ions attract the partially positive hydrogens in H2O. Note: oxygen is partially negative because it is more electronegative than hydrogen, and vice versa. Silver 1 chloride Ag++ Cl-. However, there is a limit to how much salt can be dissolved in a given volume of water. This amount is given by the solubility product, Ksp. This value depends on the type of salt, temperature, and the common ion effect. One can calculate the amount of silver 1 chloride that will dissolve in 1 liter of water. Some algebra is required. Ksp equals times equals 1.34 times 10⁻⁵. The result: 1 liter of water can dissolve 1.34 times 10⁻⁵ moles of silver 1 chloride at room temperature. Compared with other types of salts, silver 1 chloride is poorly soluble in water. In contrast, table salt has a higher Ksp and is therefore more soluble. Solubility of organic compounds. The principle outlined above under polarity, that like dissolves like, is the usual guide to solubility with organic systems. For example, petroleum jelly will dissolve in gasoline because both petroleum jelly and gasoline are non-polar hydrocarbons. It will not, on the other hand, dissolve in ethyl alcohol or water, since the polarity of these solvents is too high. Sugar will not dissolve in gasoline, since sugar is too polar in comparison with gasoline. A mixture of gasoline and sugar can therefore be separated by filtration or extraction with water. Solubility in non-aqueous solvents. Most publicly available solubility values are those for solubility in water. The reference also lists some for non-aqueous solvents. Solubility data for non-aqueous solvents is currently being collected via an open notebook science crowdsourcing project. Solid solution. This term is often used in the field of metallurgy to refer to the extent that an alloying element will dissolve into the base metal without forming a separate phase. The solver's solubility line is the line on a phase diagram that give the limits of solute addition. That is, the lines show the maximum amount of a component that can be added to another component and still be in solid solution. In the solid's crystalline structure, the solute element can either take the place of the matrix within the lattice or take a place in a space between the lattice points. In microelectronic fabrication, solid solubility refers to the maximum concentration of impurities one can place into the substrate. Incongruent dissolution. Many substances dissolve congruently, i.e., the composition of the solid and the dissolved solid stoichiometrically match. However, some substances may dissolve incongruently, whereby the composition of the solute in solution does not match that of the solid. This solubilization is accompanied by alteration of the primary solid and possibly formation of a secondary solid phase. However, in general, some primary solid also remains and a complex solubility equilibrium establishes. For example, dissolution of albite may result in formation of gibbsite. Nal C3O8 plus H plus 7H2O equals Na plus L3 plus 3 hydrogen silicate. In this case, the solubility of albite is expected to depend on the solid-to-solvent ratio. This kind of solubility is of great importance in geology, where it results in formation of metamorphic rocks.